indeed, I was at the University of Washington, and indeed, at some point, I did human-computer interaction there, but it was James who caused human interaction to become visible at the University of Washington. I started in AI, and my advisor and I started working on user interfaces that adapted themselves to their users. And we had a number of great ideas. And eventually, we came up with another one. We thought, why don't we involve actual people in our research? And that actually proved quite difficult because neither of us had much experience with HCI, and we tried to look for HCI expertise throughout University of Washington, and there were only a handful of people, and they were already overcommitted. So eventually I found a mentor at Microsoft Research, Mary Czerwiński, and then James showed up and actually created a large, vibrant HCI community at University of Washington, and they just gave a talk there 2 days ago. And when I was starting at University of Washington, there were maybe a handful of people who knew what HCI was. And when I gave a talk there were 120 people in the audience. So thank you, James. I am the Human-Computer Interaction Department at Harvard University. I share this privilege with Pao, one of my students, a survivor of Stanford. So we do quite a few things because departments have to have broad interests. So we do have broad interests. We work quite a lot on user interfaces and systems that adapt themselves to their users. This is to a large extent motivated by the observation that one-size-fits-all design practice is inherently discriminatory. By hyper-optimizing our designs for particular populations, for particular assumptions about our populations, we systematically, even if in small ways, discriminate some groups of people, and these discriminations add up. So my initial work was on adapting systems to people with motor impairments and vision impairments. I was very frustrated with the state of public discourse on accessibility because we still strive to make systems to make access possible, but what we really need to be doing is to make access equitable. If a person with impairments needs 3 times as much time as everybody else to complete a task with a user interface, and we spend 8 hours a day in front of the computers, then this 3-time amplification of the effort actually means that person is professionally or personally or educationally severely disadvantaged. So I'm trying to identify and eradicate these inequalities that arise through one-size-fits-all design. As a professor, as an educator, I became very much interested in how we teach, what it means to teach, what it means to learn, and some of my research went into this direction. Some of the original work on learning and teaching actually looked at fairly exotic domains, like learning how to detect landmines, and more recently, I brought it back into the regular classrooms. I also work quite a lot on human computation. So as Michael mentioned, I am very interested in intelligent systems, in systems that in some way exhibit intelligent behavior. For a long time, I worked on machine intelligence as the source of the kind of adaptive and intelligent behavior in my systems. But I realized that people are pretty smart too, so why not leverage human intelligence behind my interactive intelligent systems? And a lot of our recent work in this space tried to step away from paid crowdsourcing and toward what we call organic crowdsourcing, where human computation happens as a byproduct of activities that people find inherently valuable. And yet another branch of our research has to do with developing new empirical tools for human-computer interaction research. So I remember when, toward the end of my graduate school, I went to a party, met Mary Czerwiński. She pulled out her iPhone and showed me an app and said, "See this app? My daughter did it." And she's got 10,000 users. And at that moment, I realized that a motivated teenager had access to a larger quantity of data than an average HCI professor had in a lifetime. And I thought that that wasn't quite right. And I thought we should do something about it, that we should invest a little bit of effort into expanding our empirical toolkit so that, when it was right, we could do more than just run a lab study with n equals 15. So this breaking out of the lab, the expansion of the empirical toolkit is what I would like to share with you today. We've worked on a number of projects in this space. We've built a system that unobtrusively monitors people's motor behavior as they operate their computers in the wild and tries to pull out lab quality data from these natural interactions. We've obviously worked a little bit on paid crowdsourcing and evaluation of UI innovations. Then we took it kind of into the organic space, and we've built Lab in the Wild, a platform for conducting empirical behavioral research with people in the real world. And we've also started working on ways of reporting potentially disturbing results back to participants in a way that is ethical and not disturbing. And specifically, we're working with people who are doing biomonitoring, people who are discovering pollutants in your tissues and in your environments. How do you tell people what you found in their lives, even if you don't exactly know what that means? Because obviously you are measuring chemicals whose impacts are not yet known. That's the point of novel biomonitoring research. And we're bringing it back to human-computer interaction because some of the things that we measure in large-scale studies are things related to people's perception and cognition, and people get upset if a study tells them that maybe there's something unusual about how they think or how they perceive the world, and they would like to. On the one hand, they really want to know their results. On the other hand, we also need to communicate them in such a way that they understand what these results actually mean and what are the uncertainties in the science. So I would like to tell you about just two of the projects that we did in this space, and focusing particularly on Lab in the Wild. I'll convince you that the data that we get in the wild are valid. I'll try to share with you some of the insights from that project, ways that we believe are the design decisions that we've made that we believe are responsible for the high quality of the data. And I'd also like to share with you two pieces of novel research that we've done that we could not have done without Lab in the Wild. So I'd like to share with you some of the research results that were enabled by this expanded empirical toolkit. But to begin with, I'll tell you a little bit about measuring people's motor performance in the wild. It's a project I conducted with an undergraduate who is now at Cornell University, and with Katerina Reinecke, who was a postdoc at Harvard and is now a professor at the University of Washington, Seattle. So the motivation is that we conduct quite a lot of research that requires some understanding of people's motor performance. We either want to understand motor performance across population, or we want to understand how people interact with novel devices or with novel software. We can perform these measurements by inviting people in the lab, but often the scale is not quite right. Or we would like to see actually what happens when people are not in the lab and focusing entirely on this task, but what happens when they're in a real environment, interact with the computer for extended periods of time, get fatigued, get distracted, anything else. We've got a lot of ways of reasoning about motor performance data, but all of these existing analysis tools assume that we are presented with very clean data, which is actually very different from what you get if you just observe people's motor performance in the wild. The data that we know how to analyze are data that are a product of deliberate and targeted pointing movements when a person is trying to perform an input activity, a user interface activity, as quickly and as accurately as possible. But in the real world, they may be, they may be thinking very hard about the task. They may be distracted by a conversation. They may be distracted by TV. Anything else can be happening. So how can we get the clean data, the data that we know how to analyze, from the sea of interactions that we observe in the real world? So what we really want to do, the micro problem that we want to solve, is that given a movement trajectory, we would like to be able to tell whether that movement was a deliberate targeted movement or whether it was something that was affected by any kind of distraction, either cognitive, perceptual, or anything else. And given my background, I decided to take a data-driven approach. So why don't we get a whole bunch of representative data and try to figure out computationally through machine learning a model that would be able to distinguish between targeted, deliberate movements and everything else. And this proved to be a somewhat interesting task. A typical way of thinking about building a classifier, a machine learning system that is able to tell this is deliberate, this is not, is to collect data some of it representing deliberate targeted movements and some representing other movements, so movements that represents the full range of distractions that people can be presented with. If we've got something like that, we can indeed train a classifier. And it's quite easy to imagine how we can get a corpus of clean data, of positive examples of deliberate targeted movements. All we have to do is invite people to the lab and have them participate in an experiment in which they perform as quickly and as accurately as possible. But where do we get data that are only negative examples, movements that are distracted and that are representative of all of the distractions that people can experience in the real world? It turns out that such data set would be very hard to obtain. What instead we have is, observations from the real world that are a mix of both deliberate targeted movements when a person wanted to do something quickly and all sorts of distracted movements. So what we have over here, rather than having positive and negative examples, we have positive examples and a sea of unlabeled examples. What can we do with this? It turns out that there is a very rare machine learning method for dealing with such situations, and we found it and we applied it to this task, and we're able to build an effective classifier by taking lab data and by taking data that we collected in situ in the wild by building a Firefox extension. It's a fairly old project. There was a browser called Firefox then. Yes?
So before you get too deep in this, I just want to ask, your basic position in this project has been there's models that we know work, and you have noisy data, and so that in the real world that model seems to really struggle. So how do we make it fit the model? Like the obvious other question would be, is our model wrong? Yeah, like should we be maybe revising our core, like how we think about and produce Fitts law and its corollaries?
So I'll rephrase it to make sure that I get it. You are saying we've got a whole bunch of ways of analyzing motor performance data that relies on clean data produced in the lab.
Which may not actually, like this might be just evidence that that never happens.
Well, it actually does happen. People occasionally, are focused enough on a task that they're not distracted by anything else. And I think that there is value to, separating effects of different processes inside our bodies. That there is the neuromotor process that we want to study via Fitts law. Then there is, high-level cognitive processes that cause us to attend to screaming children, to think about, what is the next button that I want to click, right? Which is separate from actually wanting to click it. So I think there's value in keeping this separation. And I think rather than fixing our tools for analyzing the data, I thought it was appropriate to find ways to make our data fit our analytical tools. In this case, I thought it was the right choice. So, very quick summary of the data is that given the noisy data that we collect in the situ, we're able to filter those data with the classifier that I just described. And the noisy data filtered with our tool were essentially statistically indistinguishable from data that we obtained from the same people through a controlled experiment in the lab. There were some nuances to it. It really helped to know what targets people were clicking on and where these targets were located and how large they were. When we had that knowledge, the accuracy of our system improved. And also, obviously people are different from one another. If somebody has a motor impairment or is showing prominent age-related changes in their motor performance, that their targeted and deliberate movement will often look like a distracted movement of somebody who is younger and able-bodied. So our system also gets better if it has a chance to collect some amount of unlabeled data from a person, understand the kind of variance in that person's data, normalize it, and then perform the classification. But it works also reasonably well, even if we do not know where the targets are, and if we have no prior exposure to that person. Yes, sir?
So there seems to be an obvious issue here where if you have a large enough data set, it could be even a completely stochastic data set, and you are searching for particular patterns that you have identified in the lab, you will find those patterns because your data set is large and varied enough that they exist. And if you simply filter out to get patterns that you want to find in the lab, you will find lab data in the real world, but you have no idea what proportion of the real world data that data was. I mean, you know that. But
it was between 80 and 85% recall.
So is there in this method, does the method rely on the fact that you can't really you can't have too large a data set, or you need a certain amount of representative fit of the actual data to the model that you're searching for?
So I'm not exactly sure what the question is, but I'll give you an answer, and you will tell me whether it fits.
That's exactly it. That was a joke.
So this system is particularly, so the filtering happens on the fly. So I can filter each movement and decide targeted, not targeted, or deliberate, not deliberate. The classifier is trained only once, and then you do not need any additional data to make it better. It's ready for use. It's particularly effective for within subjects comparison. So for example, if a person interacts with two different user interfaces or with two different input devices, you can use it to really well compare these two different circumstances in the same person's life. Things get a teensy bit trickier in the between subjects comparisons, because it is possible that the thing that I'm looking for, the thing that I consider to be ideal lab-based movement, for some people will fit even within kind of the distracted behavior, and for some people, many of their most deliberate movements will not look like lab movements. But with just a little bit of exposure to a person, we're able to adapt to it.
It just seems like there's an issue of validity. As a researcher, I am searching for particular results, and I obviously don't want to bias my results. But if I have the opportunity to filter, that is, throw out data that doesn't fit what I'm looking for, then in that sense, how do I keep this method, let's say, responsible? How do I hold it accountable for the data that I've thrown out because I was searching for particular results?
Okay, so we actually validated against 5 different metrics to make sure kind of the most basic kinds of measurements that we can, and analysis that we do with motor performance data, and kind of found a solution that was good on all of them. And we assume that having validated the method against the most typical questions that we would ask, so for example, computation of Fitzgerald parameters and throughput, what we get in the wild is almost the same as in the lab. The identification of statistically significant differences among people. So wherever there was a statistically significant difference between people in the lab, we also observed those in our filtered data. We looked at recall of the movements that we knew were deliberate and targeted. So we made we performed many different checks. They worked out. So we believe that if I now take this system towards a new task, it's not optimized toward the kind of data that I would like to see for this new task. It's kind of optimized for the typical questions we ask in motor performance research, in pointing research. So I think you can trust it. So in summary, we've built a tool that is user independent, situation independent, that you can apply to perform motor performance research in the wild. One quick digression: I kind of made a big deal out of using this special classifier in our research. The reason why I want to point it out is because often when people use machine learning tools in human-computer interaction, people try to shoehorn HCI situations to the most common models used in machine learning, but often the most common models do not quite match the semantics of what's happening in the interactive system. So here you saw an example. When we collect the lab-based pointing movements, they are positive examples, but pointing examples collected in situ are not negative examples, that they are in fact unlabeled. When you bookmark a web page, it's a positive example of something that you're interested in, but every other page that you see is not a negative example of these are not pages that you are not interested in just because you haven't bookmarked them. They are a mix of pages that you may or may not be interested in, so you actually do not know what they are. When you go to Kai and you use the confer system and you star some talks, those that you star you are probably interested in, but those that you haven't touched may or may not be of interest to you. So this is just one kind of situation where the real world HCI situation does not match the typical semantics of a machine learning model, where you have to look for more exotic semantics. In some cases, you will be lucky, and somebody else will have already built a model that matches the real semantics of what's happening in your system. But in some situations, you will actually have to either build your own or collaborate with a colleague. And they'll be grateful to you because they'll have a high-quality real motivation to solve yet another new and exotic and novel machine learning problem. So now I'd like to move on to the kind of bigger part of the talk, the Lab in the Wild platform. 3 years ago, we...
Can I just ask a question?
Mm-hmm.
So, you did this motor in the wild experiment. Were there applications of that you had in the end?
We worked to deploy them with people with motor impairments, with the help of medical collaborators, and those collaborations are very slow to bear fruit. So we are working on it, but it has not yet happened.
What do you want to happen in the collaboration? Like, what do you want to learn or
So I'm particularly interested in really understanding the spectrum of individual differences among people with motor impairments. So I was trying to collaborate with people, with medical doctors who work with people with Parkinson's, muscular dystrophy, MS, and all sorts of neuromotor disorders, so that I could collect large quantities of data from people with these very unusual motor abilities, so that I could, understand what is the true dimensionality of the unusual motor abilities.
So do you want to eventually model the pointing of people with unusual motor abilities?
Yes. So one of my big interests is adapting to individual differences among people. I've built previously systems that automatically generate user interfaces adapted to individuals with motor impairments. And by analyzing the designs that my systems produced in the past, it's quite clear that the dimensionality of the space of motor disabilities is actually not as big as I initially thought. It can probably be described by 3 or 4 or 5 dimensions. I do not yet know what they are, and I will not know until I've collected enough data to figure it out. As a comparison, total aside, it wasn't until about 100 of years ago that people figured out a sizing system for women's clothing. Initially, tailors would take over 50 measurements when they wanted to produce a piece of clothing for women, and that made it very difficult to mass produce clothing for women. So NIST actually sent out measurement people into the wild for 3 years, collected lots and lots of samples, then had their statisticians work on paper for another 3 years, and they eventually figured out that you could describe women's clothing with just a handful of numbers and one discrete variable. So we want to do the same for motor disabilities. Okay, Lab in the Wild. We've built a site that hosts a large number of design-relevant behavioral experiments. People come and people participate in these experiments because they want to. Those experiments tend to be short, 7 to 15 minutes. And in the past 3 years, we've got over 3 million visitors and over 1 million completed experiments. The immediate question that everybody asks when we tell them about Lab in the Wild or when we try to publish the results is, can we trust your data? And the common assumption is that when you bring people to the lab, they behave themselves, but if you don't look after them, they will behave in ways that are detrimental to the quality of the data that you are trying to collect. So we ran 2 validation experiments to try to compare the data that we get on Lab in the Wild with the data that other people have obtained in real laboratory settings. So one of these experiments is a famous experiment by Sternberg from a long time ago, in which measures one aspect of people's short-term memory. So people participating in this experiment are asked to memorize a sequence of symbols And then they're presented with one symbol at a time, and they're asked to say, was this symbol in the set that I've just memorized, or was it not? The key finding in the original experiment is that the response time grows linearly with the number of symbols that people had to remember in the first place. So it essentially shows that we scan our working memory, our short-term memory, sequentially, rather than accessing it associatively or in any other way. And there's a very beautiful linear fit. So the first thing that we checked with our lab in the wild data was, do we reproduce this finding? Do we get a good linear fit? And we get a beautiful, beautiful linear fit. Another finding related to the original experiment is that even though the absolute speed with which people may respond may change, the slope of this fit is insensitive to training. So there are no learning effects when it comes to the slope. And again, we looked at both first-timers and people who had done this experiment multiple times in the lab in the wild, and we find that there is no substantial or significant difference in the slope. There are no prominent learning effects. Another validation, another result that we looked at is the accuracy with which people answer these yes or no questions. In the way you analyze the results of this experiment is that you throw away everyone who had accuracy lower than 95%. So we did it as well, but we actually looked at the percentage of the people that made mistakes, percentage of mistakes in each of the difficulty levels in lab in the wild setting, and in one true laboratory setting that shared these results. And we found that our participants actually made fewer errors, especially on the hardest tasks, than undergraduates who were paid to come to a laboratory and perform this task. And I'll tell you in just a couple of minutes why we think our people work harder than people that you bring to the lab and pay them. Another experiment that we did was the reading the mind in the eyes test. In this test, people are presented with just the eyes part of a person's face, and they're presented with 4 possible emotions, and they're asked to pick what emotion this face is trying to communicate. And this experiment was originally conducted in Britain. Because Lab in the Wild is accessed by people from all over the world, we're able to pick participant demographics that matched exactly the participant demographics used in the original study, and there were no significant or substantial differences between our results or the results obtained in the original study. We're also able to extend the original results. So one thing that became very clear is that this test is very culture dependent. It works very well in Western cultures. It works very differently in cultures where emotions are communicated differently in private and in public discourse. And this is controlling for the English language skill and for frequency of computer use, which were 2 extraneous factors that would also affect performance. We also noticed that there are not very big but significant age-related differences that follow the typical curves of cognitive development that show us that the theory of mind skills actually do change throughout lifetime. So we are fairly confident that the data that we collect on Lab in the Wild are reliable. When we present people with these cognitively demanding tasks, they actually are putting serious cognitive effort into memorizing these sets and working hard. And when we ask them to perform these effortful subjective judgments with reading the eyes in the mind test, they also do it honestly and well. And the question is, why is it happening? Why are participants behaving so well? One decision that we made in designing Lab in the Wild that we think is responsible for this is that we reward people's curiosity. We do not rely on altruism, we do not rely on money, but instead we tell people, take this test, find out something about yourself, and compare yourself to others. And people want to look good in their own eyes. People want to be better than their friends, and this seems to really impact people's performance. And at the end of every study, we tell them, how they did and how it compares to others. And often we try to, put it in perspective and, synthesize the data in a variety of interesting ways. And, this bribe works in a very, is not always equally successful. So, one of our study attracted 500,000 people, whereas others attracted fewer. But, even our less successful studies easily get 10,000 or more participants. So, this is substantially larger than n equals 15. Another thing that I think we do right is that now, we didn't do it initially, we make all of the potentially tedious things optional. So we tell people, please fill out this demographic questionnaire, please, please, please. And if you are lazy, just do these first 4, but we do not require it. We found that when we required it, people would, so many people were suddenly were born in Antarctica, right, or Afghanistan, or anything else starting in A. So we thought that it was better to get a smaller quantity of data, but more trustworthy data than to insist on everybody providing us with data. Depending on the system, on the test, maybe up to 1/3 of the people choose to skip some of the questions, and that's fine, because those who do provide answers, all of our checks show that the answers are truthful. And then also we provide a number of mechanisms through which participants can tell us whether the data have been in any way compromised. So for example, we always ask participants whether they've taken a particular test before. We give them plenty of opportunities to give us comments, and in particular, we ask them whether they experienced any difficulties and whether they've cheated. And they tell us. They tell us very interesting things. Some you would expect, some you wouldn't. We seem to have a very interesting relationship with substances. And it goes both ways. And we also have very interesting relationships with educational institutions. Oops. Oh, I see. All right. So with this in place, I would like to show you two novel studies that we conducted that actually allowed us to do novel science, with the help of Lab in the Wild. So the first piece of work that we did was on understanding people's perception of aesthetic appeal. And now wake up, because there's going to be a test. Are you paying attention to the screen? Okay, so watch carefully. How many of you would consider making a purchase from a website that was designed with this kind of visual aesthetics? Okay. Pay attention again. How many of you would consider making a purchase from a website that looked like this one? Okay, good job. Can I have your credit card number? The interesting thing here is not that the specific answers that you gave, but the fact that you quite confidently gave answers in both of these cases, and that they were actually different. And this effect has been well documented. Your first impression of aesthetic appeal mediates your perception of the trustworthiness of a digital resource. It mediates your willingness to engage with the resource, and even more importantly, it mediates your actual success using that resource. So if something is ugly and you encounter a problem because you experience negative affect, you will be trying the same thing over and over again. If something is pretty, you experience positive affect, you will try something different. So there are actually measurable usability effects of aesthetics. Two aspects of a visual design that impact perception of aesthetic appeal the most are colorfulness and visual complexity. So the first thing that we did in this study was to build a computational model based on computer vision that, given the design, analyzes both the spatial structure and the colorfulness of the design, and is able to produce predictions of the colorfulness and visual complexity that matches very well with people's actually subjective ideas of colorfulness and visual complexity. So building on these two, on this tool that allows us to put in a visual design of a website and get two numbers that describe the properties of this visual design, we tried to build a model that would predict how much people would like different designs given the colorfulness, visual complexity, and the demographics. So we conducted a study on Lab in the Wild with 40,000 people and a large number of designs, and we're able to characterize what's happening. So for example, for the visual complexity, there is a definite peak. The designs that are too simple or too complex are not liked as much as those that are just in the right place. And these are examples of the designs that kind of seem to fit in the sweet spot for the general population, for when we aggregate over everyone. We get kind of the same phenomenon for colorfulness. And obviously, when we start looking at individual demographics, we start seeing differences. And some of them, enforce the stereotypes. If you add color to a design, Germans get upset, Chileans cannot get enough. When you look at education, the more time we spend in school, the more boring websites we like. So our appreciation for color just decreases. So we were able to create a model that explains, almost half of the variance in the ratings of people's first impressions of aesthetic appeal. So fairly good predictor. I mean, obviously not ideal, but for a computational predictor, it's pretty good. And it takes into account both the kind of objective properties of a website and your demographics and puts it all together and makes a prediction. On the side, I told you that I was quite concerned with the one-size-fits-all design and its potential discriminatory effects. So here are some observations, qualitative observations that we've made. We've realized that, for example, the design of many of the MOOC websites are kind of hyper-optimized for educated Westerners and discriminate against people from other parts of the world with less access to formal education. These are examples of websites that appeal to women much more than men, and these are examples of sites that appeal to men much more than women. Notice that the latter two are both websites that teach you technical skills or give you access to technical resources. We want more women in computer science, but the resources that we build, appeal to men way more to women. So even before they try, we kind of already make them less likely to trust us, less likely to engage, and less likely to succeed. Just small things, but they add up. So to synthesize this study, prior research has told us that first impression of aesthetic appeal mediates perception of trust, perception of willingness to engage, and usability. It also told us that complexity and colorfulness are the key factors that predict first impression of aesthetic appeal. And in our study, we've built a model that is able to predict the aesthetic appeal of a visual design of a website. We've presented evidence of fairly large individual differences among first impressions of visual appeal across populations, and that they correlated with demographics. And we also, this study was only possible because we had access to a very heterogeneous pool of participants from all over the world. Yes, sir.
I was just wondering, when you showed us the websites, you just showed us the websites for less than a second, I guess. So do people form their first impressions that quickly?
Yeah. In fact, 50 milliseconds is enough. And I showed them to you for 500 milliseconds. So that there are prior studies that compare your impressions after 50 milliseconds and after an extended exposure, and they show that there is a very high correlation. So we form immediate and lasting impressions incredibly quickly.
How was the study run? Was it a two alternative forced choice? And how many of these did a single person have to do? And
so each person saw fewer than 20, and they saw them twice. So they saw 20 in a random order, then there was a break, and then they saw these things again in a different order. They were told that they weren't told that they would all be the same, but they were warned that there would be some repeats. And we looked at the correlation between the responses in the first phase and the second phase to figure out whether they were really making an effortful effort.
What did you have to respond to? What was the response?
The response was a 9-point Likert scale, asking how visually appealing is this website.
Between each display or summatively after all?
After each other. So you are shown something for 500 milliseconds, question, 500 milliseconds, question. And we're able to very easily tell who was paying attention and who wasn't by showing the same designs twice. Another, James.
What features are you training on for the complexity
Oh my goodness, there's...
Is it just like every feature you could find, or, you know, you're hard-coded how to do it?
There were about 40 features, so there were several previous studies that either qualitatively or computationally analyzed visual complexity and colorfulness. We built on all of them. We collaborated with Tom Ye at Boulder, University of Colorado Boulder. We implemented all of them, and a subset of them turned out to be very strong predictors of people's actual perceptions of.
So you think you could get it higher in terms of correlation?
So I cannot remember the names of the authors from whom we borrowed the features, but our correlations between predicted complexity and colorfulness and the actual complexity and colorfulness were like 0.7. So they were very, very high. I don't think you can get much higher given that people are noisy. There is no ground truth. I mean, so we chose to use people's ratings as the ground truth. I've got 4 minutes and very exciting results, so I'll move on.
Go ahead.
I'll talk to you some more later. So we ran a cross-sectional study of age-related differences in motor performance. We gave people this task in which we told them to click on the dots, and we told them that at the end we would try to guess their age, and indeed we did. Not very accurately, but we also asked them how far off were we, tell us your real age. So we had lots and lots of data. 500,000 participants did it, so we had motor traces from 500,000 people and their actual ages. We extracted lots and lots and lots of features from it. Here is a subset of them. We ran a factor analysis on them, and this actually turned out quite interesting. So as you would expect, some features predict people's speed and strength. Some things cluster clearly around fine motor control. Others reveal cognitive processing speed. But there's a separate set of features that are just related to the path quality that do not correlate with anything else. And I'll explain to you why I think that they are actually really distinct. And then errors are their own factor. So we performed this factor analysis in a variety of different ways with different assumptions, and it always came out the same. So we're actually fairly confident that there are actually 5 underlying aspects of our motor performance system. So strength, so given that we had a very large number of data, we're able to actually estimate each of these features for each year in a person's life from 5 to 75 or to 85. And we see very interesting patterns that correlate quite well with what psychologists had predicted qualitatively. So strength peaks in late 20s, and that's to be expected. There is a dip in college. We don't know why. Fine motor control improves dramatically till late teens, and then we get worse and worse and worse. Lower is better here. Cognitive processing speed, the 2 measures that we use for it are the initiation time, so how quickly you begin a movement after the stimulus onset, and how much time do you spend between when you stop on the target and when you click. So the time that you spend ascertaining that you really are on target. And these things, just like fine motor control, peak in the late teens, again, exactly what psychologists would predict. Interestingly, however, errors decrease throughout life. So, they're highest in early teens, and then as we age, we become more and more and more accurate. There are a couple of prior studies that show that older adults make different speed accuracy trade-offs than younger adults. It's a higher cognitive choice. It's not related to actual low-level abilities. And then you get the most interesting results, which is the path quality, which has a very strange shape. It seems like from early teens till about the age of 20, what's responsible for the improvement in the path quality is the improvement of in your actual fine motor control abilities. But afterwards, even though your abilities decline after late teens, your movement error and your movement variability still get better and better and better. And we think that this is where the kind of the higher level cognitive trade-off of the speed and accuracy trade-off is responsible for the results. Your errors keep decreasing. You are paying more attention to being accurate, even though your abilities decline. And this is probably what's responsible for this effect. So we conducted a large study, we were able to characterize how these abilities change throughout our lifetimes, when they peak. Very interestingly, children become better at 7 times the rate at which adults become worse. So when you design for children, within a single classroom, when you design for school children, you will have dramatic differences in motor abilities. So when you design testing situations or any other educational interventions that rely on certain level of motor performance, allow for the fact that you will have fairly vast differences. So make sure that people's success does not depend on their low-level motor performance abilities. And the one interesting novel finding is that there's this aspect of motor performance, the path quality, that seems to depend on 2 separate factors in interesting ways. So this is the end. We've done a number of projects trying to expand our empirical toolkit. I've shared 2 of them with you. I've showed you 2 studies that we're able to run only because we've expanded our toolkit. And that's it. So,
Just wondering, in the second experiment that you did with motor performance, wouldn't there be a significant difference between users on a laptop with a touchpad or whatever, and users using a mouse?
yeah, so these results control for that. So we had touchpad users, we've got mouse users and other input devices users. Very interestingly, we also saw operating systems related differences. So the operating system correlates with the kind of age of the hardware. So typically, more recent operating systems are also running on more recent hardware. We saw a very interesting trend where on Windows, people's performance was getting worse and worse with the later and later releases of the operating system, whereas on the Mac, it was getting better and better. Trackpad tends to perform typically worse than the mouse, but Apple was able to bring the performance of the 2 to par. They were actually as good, whereas on Windows, the trackpad performance was diverging from the mouse performance. So yeah, there are very interesting differences related to both the hardware and software, and we saw them and we controlled for them in these results.
Is that hardware self-reported?
So,
Gajos didn't tell you that.
so we did, yeah. So whether they were using a mouse or a touchpad was self-reported, and there are very clear differences. Like when you look at the data, you can clearly see what's mouse, what's trackpad, and as far as we can tell, people's self-reports were accurate. So
it seems like such a powerful tool when you were able to replicate these studies cross-culturally and observe like population differences. But we also know, and you mentioned that your incentives will really affect your accuracy. I was curious if you knew of any work in differences in the effectiveness of incentives across cultures and whether that would play a role in the differences in accuracy we see across cultures.
Talk to the guy behind you.
Oh. Okay.
So I believe they exist. Yeah, and we can actually, in our motor performance data, we actually see substantial cultural differences that indicate that in some cultures people preferred accuracy over speed, and in others they preferred speed over accuracy. So that actually directly shows that what people are incentivized to do and how they're incentivized does differ, but I cannot characterize these differences. Manish.
Okay, so you showed us some experiments that you've run in the wild, very nice and interesting results. And then you also spent a little bit of time talking about some of the findings you had about how to run experiments in the wild. Do you, have you tested those things? What's the, again, kind of what's the goal for Lab in the Wild, and where do you want to take those?
Okay, so there are 2 questions. So how do I know that the reasons that I told you are true? Some of it we know by analyzing the social media posts about Lab in the Wild and the things that people chose to say. Some of it we know from the analysis of the comments. Some of it is kind of our own speculation about the causal mechanisms.
But you haven't run a test, with and without the survey, or with and without the reports about your personal scores.
Yeah, we felt that there were bigger effects that we wanted to measure first, but right now we're building self-analytic kind of A/B testing infrastructure so that we can precisely answer these questions, both in how we frame the incentives and how we order things at which places people drop out. How does the wording and the choices that we make affect people's self-reported and real performance? Yes, we're doing all of these things. I mean, this is just such a fertile ground. We can do so many different things. So we're also actually interested. So we've kind of replicated a number of COXI traditional experiments, but we're also trying to push the boundary of what we can do in this space. So Power had attempted to run a creativity study in which people both were creative and provided judgment on other people's creative outcome. That's something that hasn't been run in this kind of setting. We are looking at bilingual studies. We are looking at a number of other things that have not yet been run in large-scale settings.
So, yeah, very much kid in the candy store kind of question here. I'm staring at your subtitle, Tools for Large-Scale Experimentation in HCI. In many ways, I feel like there's a huge opportunity because I think you've done some of this work, but I feel like what you've described is largely tools for large-scale correlation in HCI. And like the opportunity to run randomized controlled experiments that are manipulating things in many ways are the gold standard because you're owning this platform, you have this opportunity. So I just wanted to probe some of your motivations in the particular studies you ran, and in which cases you were looking for, what guided you toward those versus things that were potentially more RCT style experiments.
So the newer experiments are, within subjects multi-condition experiments. So I obviously have an adaptive user interfaces experiment that is presented as a multitasking experiment because it combines, varying levels of cognitive load with different kinds of adaptation. So we are rolling out the true experiments.
Do you see what have we missed because we couldn't do that you feel like you can get at now? Like obviously there's just a huge range of stuff, but like what do you think is so you're the kid in the candy store because you and Federated I guess have this platform. What are the most attractive questions in HCI that you think we haven't been able to get at that if you had a small army of interested graduate students you would go after first?
Okay, so first thing I have to say is that we're working very hard on opening up Lab in the Wild, and we to other researchers, and we are currently recruiting people who are willing to work with us on beta basis to figure out how we should structure this relationship. So we do have several external researchers working with us. So we are opening up the candy store. Katarina is incredibly excited about cross-cultural research without having to go to Rwanda every time she has a new question. And she has been able to conduct cross-cultural research, which is quite interesting because in different countries you sample a different skewed subpopulation and you have to correct for that. I am very excited about understanding the breadth of individual differences that are present among people, understanding how they impact people's engagement and success with interactive systems. And I'm interested in finding opportunities for making access to digital resources fairer and more equitable. And in both of these cases, we are relying on the fact that we are accessing a much more diverse and much more representative population than we would have if we only brought undergrads into a lab. So it's not just the scale, it's the diversity of the population that has been particularly important to us. And the very important aspect of all large-scale experimentation platforms is not just that your N is larger, but the fact that the theory to experiment cycle is shortened. So as you see changes that you need to make in your experiment, as you see other conditions, as you see other sub-questions, you can turn these around incredibly quickly, and you can produce your science so much faster. And you can go after riskier questions because the cost is lower. I believe I'm allowed one more question, and the gentleman that was...
I was wondering, you saw a lot more variability in both extremes of age, and I was wondering if any of that is due to the fact that you probably have smaller numbers in the sample at the ends?
Yes, that was precisely that. So the variance, the standard deviation wasn't much larger in those areas, was a little bit larger, but the sample sizes were much smaller. Okay, Juhad, last one.
Yeah, quick question. Just to follow up on Michael's point, do you think the way we run experiments with interactive systems, for instance, if I were to write a Pi paper and recruit 12 people around campus to do some tasks that I give in using my system, versus having potentially 10,000 people on lab in the wild using my system. So I'm curious about where do you think the right balance or the right direction as a community that wants to produce reproducible results of science?
So every tool has different properties. So I think this tool is particularly valuable if you want external validity, if you believe that your results really depend on having a more representative sample than undergraduate students. I think it's very important, very useful if you go after small effect sizes, right? Because you need much larger samples to detect small effect sizes. It's very helpful if you want to compare a large number of conditions, right? Because with a large pool, you can run mixed within between subjects experiments and analyze 16, 20, 100 different conditions and kind of do that kind of exploratory study. So I don't think you should do every experiment on lab in the wild, but I want you to have a tool like that in your toolkit so that when you have an empirical question, you can make an informed decision and pick the tool that is right for the problem and not pick the only tool that you have. Thank you.
All right.